Okay, so welcome everyone to another talk in the Northwest Database Society series of Columbia. Today it's my great pleasure to introduce Professor Dan Olteanu. Dan was a professor at Oxford and he moved to the University of Zurich a few years ago, where he leads the database lab. So Dan is very well known for several contributions at the intersection of database theory and systems. Perhaps some of the best known are those where he applies, where he optimizes machine learning over databases by combining optimization techniques, integrating optimization techniques for databases and integrating them into machine learning pipelines. Also on probabilistic databases and incremental view maintenance, a fundamental topic. But he is absolutely best known for his invention of factorized databases, which is a pretty deep concept. He invented this like 12 years or 15 years ago. And finally, the systems community starts to catch up with this, and several systems group are actually, looking at the papers or papers that people wrote after they write down papers. So today we are so lucky to have Dan himself telling us about factorized databases. So Dan, take it away.
Thank you so much, Dan, for the invite. It's great to be here. I also was blessed with fantastic weather, right? Of course, it did drizzle a little bit today, but past days we had sun. It was blazingly strong, and I was in the office, getting a tan. And but I also walked around the campus. The campus is fantastic. So yes. This work, indeed, I started in 2011 when a student, Jakub Zawodny, I had this idea and I was looking for a student, and I was lucky to have a student who came already with funding. He wanted to work with Samson Abramsky on category theory, and he found it a bit too difficult. He wanted something more somehow algorithmic, and then he shopped around, and I convinced him about this idea of factorized databases, and then we started working on it. So what is this about? So there are actually two simple observations that underline this work, and one is that if we look at the results of queries, right, we realize that some values are repeated many times. And this is in the nature of the joins. The joins, by their semantics, force you to have these repetitions. Yeah, but there is some redundancy, right? I mean, in database theory, people look a lot at removing redundancy in the input data by means of normalization theory and so on. But when it comes to the query answer, suddenly, it's not anymore an issue, right? So the thing is, can we come up with something like normalization theory, but for output of a query, not only for the input of the query? So that you can take it like this, yeah? And I will show you examples where blocks of rows and columns are repeated many times, yeah? So the question is, can we get rid of that? So then the second observation is that, yes, this redundancy can be avoided in a lossless manner. That is, you don't have to have a lossy compression. And this is by means of what we call factorization, which reminds of the arithmetic factorization you might be used to from primary school. Like, when you say 2 times 5 plus 2 times 6, you can say instead 2 plus 5 plus 6, right? So it's exactly the same, but now applied to data in databases. Okay, so we want to repeat these blocks to avoid the repetitions, to only have them once, but not only in representation, but also in computation. We would like to compute them once and know that they are used several times. Now, why this work actually became interesting? Because of two reasons. The first reason is perhaps not so interesting to the systems people so far, is that if you give me the query and the data, let's say I have a join query, I can compute the factorized representation, this compact representation of the output, optimally, worst case optimally, from the input, okay? So that is good because it means that, well, basically you take time proportional to its size to compute it, yeah? Modulo some logarithmic factor. And the second one, which actually, made it very interesting to the community, was that somehow this compression is at the right spot between, let's say, having something very compressed and still allowing to do various tasks directly on the compressed form, right? So many tasks can be computed directly and efficiently on this factorized data. And in particular, we can do SQL aggregates in query evaluation, but we can also enumerate answers to the query as efficiently as if you'd have them presented to you as a table. Yeah, but we can also sample, right? If you want just some tuples in the output, you can just sample directly on top of this. Then a long line of work on which I worked a while back, and but it wasn't only me. There were also people like Arun Kumar at UCSD and others. You can train machine learning models and even solve linear algebra over relational data in a factorized way, right? So that is, for instance, if you have several tables which you join to construct a data matrix on which you want to train or which you want to do some, sophisticated linear algebra computation, instead of doing that, you can actually basically use a factorized compact representation of the join on which you can do this operation and obtain the same result. But it can come much faster and also asymptotically with a lower complexity. And then a different topic that also benefited is that of maintaining queries and models under data updates. So you do changes to the data, to the input data, and you want to propagate these changes to the output. If you represent this output in a more compact way, it turns out that you can maintain more queries with just a constant time update than you could do if you just represent the data, the result of the query, just as a relation, right? So for this reason, it also made a big splash. But more recently, I realized I didn't work on graph databases, but there are people like Semi Seselioglu, for instance, at Waterloo, who show that database workloads some perhaps mute the people. So yes, so you will see why. I will try to say towards the very end a little bit from his presentation of his startup Kuzu on how he uses factorization for that. And then there are ways to also factorize the provenance of a query and use it to explain, for instance, why certain records are in the output of a query, or to calculate something called fact attribution using Shapley value or Banzhaf values to basically compute how relevant an input tuple is to the output of a query, right? And these things can be done by exploiting the provenance of the query, but you can do it more efficiently if the provenance is factorized. And then also by factorizing provenance, we used it in probabilistic databases to explain, for instance, some of Dan's result on linear time computation for hierarchical queries in probabilistic databases. It's also based on the same idea that this provenance can be factorized in a form that is so compact so that every input tuple contributes once to that output. So then everything becomes independent in the output, and then you can compute efficiently probabilities. Good. So let me give you an example, but this is captured a bit here, right? By if you have such a table, you realize that some values are repeated, yeah, and then you would like to avoid this repetition, right? So you want to compress it so that, for instance, England Child, which is a pub in Oxford, right, where Tolkien used to go, yeah, is represented only once, and regardless of its orders. Good. So for that, I take a very simple example of 3 tables, encoding hypothetical ordering of pizzas by my team, Ahmed Hauge Nils. So in orders, you see these customers ordering on certain days the different pizzas, Basilia in Hawaii. Then we have a pizza table with ingredients of different pizzas and then prices of the ingredients, right? And we want to join them. So if you join them, the natural join, which is of course between orders and pizza on the pizza column, and in between pizza and ingredients on the ingredient column, you get something like this, right? Here, what you see here on the slide. Now, I don't show the whole result, but it's enough to realize that, for instance, Basilia here appears many times, that garlic, mozzarella, or garlic appears several times, mozzarella appears several times, and so on. Ahmed appears many times, and so on. So can we get rid of it, of this redundancy, and how can we do that? Well, if you look closely enough at this table is nothing but an algebraic expression in relational algebra, right? Where every record, every tuple can be seen as a Cartesian product of little relations, right? That have a single column and a single row, like for instance, garlic, right? Or like basilia, or so on and so forth. And then because we have several records, you can think of having a union of their representation, right? So now we are in this algebraic framework, and now we know what it means to essentially apply factorization, right? We can easily, because we understand that there is a distributivity law of, for instance, Cartesian product over the union, we can then factor out common terms. Yeah. So this is exactly what I'm doing. So, for instance, I can factor out basilia out of all these expressions, and then I can factor out afterwards, let's say, out of the remaining expression, Thursday out of these three, and Friday out of the next three, and so on and so forth. There are several possible ways of doing this factorization, and the question is, of course, which one would be best? Yeah, and this is some work I've done, 13 years ago, where we try to understand what would mean asymptotically the best. There has been follow-up work actually last year, where people showed that if your tables are binary, then even though I look at a certain restricted space of possible factorizations, this is optimal. So you cannot do better even if you try your hardest, right? But for general relations, what we do is we guide our search, for a factorization on the structure of the query. So we try to look at factorized representations, these factorized relational algebra expressions that follow a particular structure which is inferred from the query, because it's much easier to reason about the query, which is small, extract from it some structure, and then use that structure to essentially factorize your data. What is the structure I'm talking about here? In this particular slide, you see this. You see that I decide to first group by pizza, right? And then for each pizza, I represent on one side the days and the customers, and on the other, the ingredients and the price. What does it mean? It means that effectively, customer and day is independent. This information is dependent from ingredient and price given a particular pizza, right? Because, the pizza has an ingredient regardless whether I buy it or you buy it, if it is a fixed pizza with a given name. And similarly, we'll see later that the price for an ingredient is the same regardless whether that ingredient is used in different pizzas. So this is basically the conditional independence that you can extract from the query, which is given by the actual joins you have in the query. The joins tell you join on pizza, so this means that if you fix pizza, whatever comes in a table is independent from what comes in another table, right? So the actual instantiation of our factorization of the data, right, using that particular variable order is given here. So I have a union of two pizzas, because in my data set I only had two pizzas, Basilia and Hawaii. And for Basilia, for that pizza, on this side, right, on that branch, I have the days with the customers. On the other, I have the ingredients with the prices. So what happens in relational data bases these days is that this Cartesian product is made explicit. So you just combine all sides from here with all sides here, right? But here, what we try is to keep this Cartesian product symbolic. So we don't really materialize it. And the tricky thing is that non-materializing will not cost us for subsequent processing, as I will show you. I will try to convince you afterwards, like doing aggregates and so on. Because this one has no other conditioning, has no other, trick that comes with it. It's just that it says everything from here is combined with everything from there, right? So the culprit of this blow up in the size of the joins is exactly because of these Cartesian products, because ultimately an inner join, a normal equality join, is nothing but a union of Cartesian products. For different keys, for each key you have a Cartesian product, another key, another Cartesian product, and then you take a union of these things, right? So we try to avoid these Cartesian products whenever possible, right? Now, a different factorization may be possible, of course. I could decide to, for instance, root it a day. and then have pizza ingredient price on one side and customer on the other. So there are many, many possible ways. There are many ways you can express the same information, the same table, but with different factorizations, which is exactly the way you think also of Boolean functions, right? You can factor them differently, but they still represent the same thing. Okay? So the question we asked a while back is exactly this, how can we decide on the worst case optimal one, right? And this is one result we had back in 2012. Yes, Mo.
Then so you just said optimal a few times here.
Yeah.
Is this about the representation? And if it's about the representation, do you care about the number of nodes or the depth?
We care about the number of values, right? You want that to be asymptotically the best you can, yeah. So good. We can go further with compression. I already mentioned that price depends on ingredient and doesn't depend on the pizza, right? So if you fix an ingredient, then price and pizza become independent, right? So they are both conditionally dependent on ingredient. What does it mean? It means that, for instance, a tomato will come with the price 4 under Hawaii and under Basilia. So we can, in fact, share this value 4 here. We don't have to represent it several times. Now, of course, this saving is modest. It's just a value. But imagine that, for some queries, it could be an entire relation, something very, very large, which will avoid repeating. Yeah. So we can do this sort of caching, which actually asymptotically makes a big difference, in fact, right? So one result to tell you something about, let's say, a theoretical result is that if the joint query is acyclic, then the factorization you have here is actually of size linear in the size of the input data, right? So regardless which join you have, as long as it's acyclic, this representation here will be of linear size. But if you represent it as a table, it could blow up. It could be very large, right? So that's basically what is a bit appealing about this. Because you see, a major problem in various types of computations with queries in databases is about this amplification factor that joins can give you, right? It blows up. And then, especially if intermediate results are very large, only if at the end you get something very small, the question is, can you avoid this intermediate blow up? And that's a way, for instance, to avoid that, which has been used recently, for instance, in a paper by Neumann in VLDB in last year. Yes.
And in this example,
yeah.
Pineapple also happens to cost 4.
Yeah.
Why do you not connect pineapple to that 4?
Yes. So So we have here 4. We have here 4. Why wouldn't I represent 4 once? So so far I only look at the structure from the query, and the query doesn't know that that particular data instance has pineapple and tomato with the same price 4. But clearly we can go further and do a more instance-based compression where we realize that also such things appear. Such compressions would be like for OBDDs, for ordered binary decision diagrams, right? Where you go bottom up, and wherever you realize that some subtrees are the same, you represent them only once, right? So it is possible to do that as well, but that requires a subsequent pass. For us here, we just know this, and knowing this, going bottom up, we can already compute this, right? We don't need to care about the data. We know that it will look like that the shape will be that. Good. So a question. So I remember when presenting this to some UC Berkeley guys a while back, they asked me, okay, compression, but is this better than zip, right? Because zip is actually the most used package out there, right? If you look at the libraries, what is the most used library, everywhere, on all the devices is the compression, the zip library, right? What is the second most? Is SQLite, yeah? Here we try to combine both. So what we did is that we actually found a way to scale up the tiny example I showed you before. We introduced more pizzas, more orders, and so on and so forth. And then we said, let's actually see what is the size of our factorization versus if we would take the result of the query and we just zip it, right? And we zip it with the best compression factor, which means essentially we allow the most memory for gzip to use, so to find repetitions, over a larger window. And this is gzip compression level 6. And what we realize is that our compression ratio grows like this. This is a logarithmic, a log scale, right, on the y-axis. And but the GZIP, if you look at the compression ratio, basically is rather modest. It does compress, right, but it doesn't compress essentially exponentially as it is done in our case, right? And then what you see here with the blue line is we apply GZIP to the text format of our factorized file, because we actually dump it as a text format and not as a binary format. So there is something, because it converts. Imagine you put something in text and then each digit will take a character, right, instead of being compressed as just a number, right? So there is some compression you can get. So there is in fact something which shows that taking advantage of the structure of the query can make a big difference. And GZIP cannot see these sort of repeating patterns that can come arbitrarily later in the future of the file, right? So that's an important aspect to take into consideration. Yes.
But Dan, this is not very fair to GZIP, because it's difficult for GZIP to compress row-oriented data, but it's very easy to compress column-oriented data. And this is what column-oriented databases take advantage of.
Okay, so what I could do then to make the example a bit better is I could actually represent the data column by column, right? Put it still in a file and then give it to GZIP to compare.
Yeah, no, but I think I would go one step further, because if we care about compression, then we want to go to the original set of 3 tables before the join.
Yes.
Right, we just kind of remember that we want to join them, but we start with those 3 tables, and each one could be stored in a column format, and then each column could be compressed with GZIP or broad length encoding or whatever other compression method.
So you are right. So there will be then a much better gain there. The issue is this, however, that you can think of this factorization as being a compression which is not only vertical, right, but it's a combination of vertical and horizontal. Whereas columnar-oriented storage is only vertical. That is, for me, vertical would mean this union of these values. I could compress these ones, I could compress those ones, and so on and so forth, right? And there are approaches we tried where we looked at the values in a union, and then we tried to compress them as well. This here is already compressed in a way because you know that these 3 values appear, well, 2 times, right? So we just represent them once. But you see there are nesting levels, right? There is a union and then product and then a union again. So this does not happen in a columnar storage where you have just the whole column.
That's right.
Yes,
That's part of the reason I was thinking that if you want to go for compression, you want to compress before joining anything.
Yes.
Right, because after join, this is where you have more of the replication that you can in fact factorize out. If you go back to the original tables, then there's kind of less to factorize out.
But the goal is to store the output, right? And then compressing the inputs, you still have to get the answer, have to decompress everything,
and you have
run
to
the join. Because you can't do the join over the compressed data.
Right.
So one thing is, when I visited MIT a couple of months ago, I discussed with the guy who, I'm sorry I forgot his name, who a postdoc of Mike Caffarella, who did his PhD on compression in columnar stores. And we discussed about combining this structure compression with a more value-based compression, such as the ones you actually mentioned, right? To get the best of both worlds, in fact, right? So this is something we could investigate, I guess, in the future to see how this works. Okay, so for real-world data sets, we got this data set in the retail domain from that time was logic blocks. So we have a big inventory table with 84 million tuples in sales, and then we get census, location, clearance, promotions. All joins here are key foreign key joins, are not many too many joins, right? But nevertheless, what we realized is that we achieved actually quite good compression factors. So of the natural joins of this table. So if we join inventory with census and location, we get something like 26.6 compression factor, right? If we join inventory, sales, clearance, promotions, we get like 160 times compression. And this compression carries over to whatever task, such as the ones I mentioned before, like computing aggregates, over it, right? Good. So let me actually mention a couple of applications. Before that, I would like to say that there has been also quite some systems effort on this. For instance, in query evaluation, we developed our own prototype FDB, factorized databases, then LMFAO was layered multifunctional aggregate optimization engine. Then in Umbra, very recently, there is an implementation of factorization, and in DuckDB, Peter Bunch and some student implemented factorization to see how it performs, and it does perform actually faster than before. For maintaining queries under updates, we have our own prototype FIVM and the relational AI. I work with the guys there to carry over some of our ideas into their systems. So some of this factorization happens now there. Graph database engines, at Waterloo developed GraphFlowDB, and now it became Kuzu, the commercial database engine for graph databases. And then in query provenance and probabilistic databases, we developed ABMS and Sprout. I deal with my students, but then, for instance, Boris Glavich did a PUG system that uses factorization internally for explanations using provenance, and NLProf by Daniel Deutsch. Then there was a term coined by Arun Kumar, right, from UCSD. He called it factorized machine learning, to do basically factorized aggregation the way we do it, but now for machine learning. And then he came up with Morpheus and other systems. Eugene Wu, Columbia, the Joint Boost, which also uses factorization. We also implemented our own systems. And for linear algebra, Trinity by Kumar, and we did Figaro system. So there has been a lot of work trying to use this idea of factorization into systems as well. And they all show to some extent that there are benefits to be had. So let me give you some examples on how we can actually exploit factorization for various computations. So first of all, for aggregates. So I give you back the factorization I showed you, right? And now think that I want to compute the count star, that is the number of records in the output of the query. But now the output is represented like this, yeah? So one way I can look at this is to say that this is an expression that uses basically a particular semi-ring, right? Which is the union and Cartesian product semi-ring, right? All I can do is to change the semi-ring to have a sum product semi-ring where the elements now, these values that were here, I map them to 1 because I just want to count. And if I do this, right, then as I said, every product becomes a multiplication of numbers, every union becomes a plus, the numbers become 1 everywhere, and I run bottom up on this and I just do the operations. And then I get the exact count, right? So the count now can be done in one pass over this representation. But I can do something more sophisticated. For instance, I want to do some price group by pizza. So for each pizza, I want to know the amount of revenue, in that, in my database, for that pizza. So price comes in a table, pizza comes in another table, right? So what can I do there? So what I can do is I can do exactly the same as for count, but now I say, because I want to group by pizza, pizza is not turned into a different value. I just keep it, I leave it the way it is, right? And then the price, which I'm interested to sum over, I keep it the way it is. Every other value is just mapped to 1. And then, again, I change the semi-ring to a sum product semi-ring. And then once I run over it, I do 1 plus 1 is 1, and so on and so forth. When I am at Hawaii, at the pizza, I create this sort of map, which tells me that now Hawaii is mapped to, will be mapped initially to 1, and then I multiply with 32, so it will be mapped to 32. The computation here proceeds similarly, and I get 36, and then Basilia will be mapped to 36. So we have a way to combine both group bys, and what we did basically a lot is to allow very many aggregates with different group bys to be executed together over the same representation, to get them very, very, also to get some shared computation. And this was primarily because of in-database machine learning. So what we learned when staring at training tasks for machine learning is that, because I am a database guy and I look at these problems, I see database problems everywhere, right? So what I saw when I looked at the training machine learning models, I saw a lot of aggregates that need to be computed, but many, many aggregates, right? So in particular, I will show you one example for a very simple model. So I look at linear regression and I will show you what type of aggregates I see there. So what do I want with this training of a linear regression model? Imagine I have here X as a matrix, which is defined by my join over the database, right? Which gives me all the features like size, bed, number of beds, year, region, and so on and so forth. This would be the parameters I want to infer. And this is basically the output I have in the data. So I want to find these parameters such that this is as close to equality as I can, right? And you typically do the square, you take the difference between this and you take the square, and then you try to minimize that, yeah? Okay, so here would be the features X, this is the label Y, but they are given from the data, from my data that resides in databases. So what do I do, for instance, if I use gradient descent? I say, I start with some values for my parameters theta, right? And then this is essentially the gradient, right, of that square loss function, which essentially says you have to take the X transpose X to compute something here, where X is your data, which would be the join result, right? Y is the label, so it's a vector of all the labels. And this alpha is some learning parameter, right? Which typically is not fixed. It changes as you get closer to some convergence, because this one will converge, the problem being convex. Yeah. So what do I have to do? If I look here, what is the data part? The data part is X and Y. So effectively, if I would be able to compute X transpose X and also X transpose Y, yeah, and I compute it once, I can do this for all the iterations. So I fix it, I compute it once, and after that, I let this fixed point computation run until I get convergence. This means effectively that I have to compute what is called the covariance matrix, which is basically this matrix, transpose and itself. Let's call this Z. So Z transpose Z. What is this Z transpose Z? So Z transpose is like you take essentially, you'll see, you take essentially a column in your data in the result of the join, and you multiply it, you do a dot product with any other column, right? In your join result. So the columns representing the features, right? But you don't want to compute the join and after that take this dot product, because this would be too expensive. Instead, what you'd like to do is to push this dot product computation past the join. So what you do effectively is what we do is we factorize the join, and after that we do the kind of aggregates I showed you before to compute them all together in one bottom-up pass over the factorized join. And that's it. So these are the aggregates we compute. So this is basically the intercept, right? It's sum of 1 times 1, which tells you, it gives you the count, right, over the join. Then this one essentially multiplies 1 with Z1, 1 with Z10. This Z1, Z10 are the features. Then you multiply Z1 with 1, Z1 with Z1, Z1 with Z10. So any pairs, right, of two features, you have to take the dot product of their corresponding columns. So this is what happens. And you want to do this over the join. Now the join being factorized, these sums, we know how to solve by means of what I showed before, right? Okay, so let's actually take this as a matrix, as the covariance matrix. We know that it is symmetric, so the bottom part you don't need to represent. So what we have here is that we have to compute the count. We have to compute some vectors, like sum over Z1, sum over Z2, sum over Zn. And we have to compute some matrix, which is sum over Zi times Zj, right? So these are the quantities we have to compute, right? So these are the aggregates. So what we did is that in our factorized representation, we go bottom up, and instead of computing a single aggregate, we now compute these composed aggregates bottom up. And once we reach the top, then we already have our result. Okay, that's one thing. But we do a little bit more than this. We realize that we can define an algebraic structure called the ring. We call it covariance ring, which essentially says that over these triples of count, vector of sums of the features, matrices of sum of pairs of features, right? We can define also neutral elements, right? For instance, the count could be 0, in case we want to sum such an element with another element, right? It could be the vector of zeros and the matrices of zeros, right? And then for the, let's say, neutral element for multiplication, if we want to multiply such guys, if we can multiply with the count of one matrix of zero and the vector of zero and matrix of zero, we essentially get neutral for multiplication as well. So now all we have to do is to define what means a sum and a product for such elements. And I will show you visually how this is like. So imagine that I have two elements. This is A with the count, the vector, and the matrix. This is B with the count, its vector, and the matrix. How can we do summation? Summation happens like this. We just sum up the counts. We sum up the entry-wise the vectors and the matrices, right? If we want to do multiplication, then you multiply the counts. You multiply every vector with the count from the other element, and then you sum them up. And here, you multiply the count from one side with the matrix from the other, and that would be here and here. And then here and here, what you do is outer products of the vectors of the two sides, right? So why did we go to the length of doing this sort of ring? Okay, just because, it's theoretically pleasing? No, it's because this allows us to define inserts and updates. Because A plus B, let's say A is in fact, let's say, you do a change to the input, right? And that is an insert. That insert, that A, could be represented in such a form, and then you can add it to whatever you computed before. If you want to do a deletion of a tuple, that can be represented as well as an element, and you can then take deletions. Because ring allows us for every element to have an inverse, right? So by doing this, effectively what we achieved is that we now can maintain the models under updates to the underlying data. Okay? So what we looked at the effect of this. So here what you see at the very top one is the throughput of our system and different other systems. Throughput means how many updates can you process per second. Yeah, and we compared against the DB Toaster, which is a state-of-the-art system for incremental maintenance, and one IVM. This is the classical IVM, classical incremental view maintenance approach, the maintenance approach that is most used in databases these days. Yeah, which does it by means of delta queries. If you heard of delta queries, yeah, and what you see is that if all features are continuous, this is the blue continuous line you have here. So we basically do it more than a million updates per second on one machine. Yes.
Just to confirm my understanding, when you say updates, you're talking about the underlying data once you've trained the machine learning model.
Yes. You train the machine learning model, and now you basically change the data, input data, and you want to propagate this to the model.
You want a new model.
You don't want a fresh model. Right. Yes. Because you don't want a stale model. Sometimes in certain areas you want the model to be fresh every few seconds, or you don't want to be fresh like at the end of the day, right? Because it's important. And this is basically what we can achieve for that specific model. If you allow for both continuous and mixed, mixed being categorical features. Categorical features are treated, I don't show here, but the same way you do the group by, because you cannot really sum over a category, right? You group by it, right? And then you sum over the other feature. And then in case you allow categorical ones, you have to also deal with this sort of maps between a category and some quantity, some numerical quantity. So it takes a bit more time, which means that the throughput is not as high as this one, but still is very high there. And so we did basically 125 million inserts here in batches of 1,000 at a time. And we put it in the system. The classical IGAN can work until the very end without timeout, but in case of also allowing categorical features, it stops early. And DB Toaster stops much earlier. It cannot process the whole thing. And this is the memory perspective. So memory here for DB Toaster is more. Why? Because DB Toaster takes every single aggregate and maintains it separately using different views. Whereas we do everything together by means of this ring. And this is where we stay, which is very, very close to classical IVM, which is essentially delta query. So we don't materialize anything. Okay. So that's basically to give you a sense that you can go a little bit further, and you can also do maintenance on top of that. So now let me actually say a few things. Well, we looked at, in very many papers, at very many types of models. Of course, we didn't cover everything. So in particular, linear regression, we considered under a variety of loss functions to give different behaviors, not only square, the one I showed you, square loss, but Huber, Scalene, epsilon, insensitive, ordinal hinge. And we did a lot of other models as you see them here. But we also applied the same idea to do matrix decompositions, where the matrix is defined by the join of the data. So you take the join part away, the keys away, and everything else, which is the data, is the data matrix you want to decompose. And we looked at QR decomposition, the singular value decomposition, PCA, low rank decomposition, and all can be done in this form. Good. So now let me say a few words about graph databases, right? I have a little bit of time. So this is basically based on work that Semi did in the context of his Kuzu system. He came to Zurich, gave a talk, and I was surprised to figure out that he actually uses factorization. He did tell me actually 10 years ago that this is a good application to graph databases, and I said, yes, do it. And then it took him a while, but then, he's there, and I'm very, I have to say, impressed by actually the result of his system. So imagine this query. This is a query written for graph data. So here in graph data, you specify a pattern to match for paths in graphs, right? And this is basically saying, I want 3 nodes A, B, and C that are connected like this, where B should have the name Liz, and I want to return the ID of the first and the last. So I want to return such pairs in such cases. Now, what happens in graph databases is that these paths, to traverse them, effectively means if you have an edge relation, right, you have to do self-joins of the edge relation with itself. But then these joins are necessarily many-to-many joins, yeah? Because, I as a node have many neighbors. Each of my neighbors may have many neighbors. So when you start, traversing, it blows up very easily, right? So in particular, if we have, let's say, about 100 neighbors on average per node, then we get something like 100 to the power of 2 combinations to generate for this path, right? Because you have one hop and another hop. So you basically take 100 and then another 100, and you combine in worst case, yeah? And then you have to search, of course, for the B's that are Liz. So let me show you basically what he does in his cider paper. He says, okay, look, consider this graph. This graph says this. I have 2 nodes, L1 and L2. L1 has 100 incoming nodes, edges from nodes, and L2 also 100 of them. And each of them has 100 others coming out. And they actually also share some of the out and the in ones, okay? So in traditional processor like Neo4j and the others, what happens is you get a lot of redundancy, yeah? Why? Because, okay, they will be smart. They will say, okay, this is our plan. For the query, you say, I will first scan B because I have this condition. And then I get Liz. So if I have this representation for B, I say only Liz, which is L1 and 2 for B, would have the mask 1. Everything else would be 0, right? So these are the only nodes for B. Now, if I want to, I have to extend A and extend C. What does it mean? It means I have to, from that B, to go and find all the A's for every B. And then for every B and A, I have to go and find the C's. So what happens effectively is exactly the behavior we've seen before, with the number of neighbors being 100. Namely that for L1, you have Liz here, you have 100 A's, but for each A, which is U1 here, you have 100 of C's. Yeah? And then similarly for L1 and Liz, you have for U2, you get again 100, and so on and so forth. So you get this blow up. So what he does instead, he says, well, instead of having this flat representation for the output, where effectively I have this Cartesian product between A's and C's for every B, I have a factorized representation where for B, Liz, right, with name Liz, I take a Cartesian product with the A's that match, right, which are U1 to U100, and the Cartesian product with the C's, C1 to C100. And similarly for L2 Liz, I have a product with U100 and U199, and then the product with these C's. So we have basically suddenly from 100 to the power of 2 100 plus 100 combinations in the representation. So this is why this is basically based on this conditional independence of the variable A and C given B, the one I already mentioned to you before. So if you fix a B, A's and C's are independent of each other. So how he does it is like this. He has this plan that does it the same with extend A, extend C. And then he says, well, I construct a so-called factorized vector for the B's, which is basically this vector with B1, B being L1 and L2. Then for every B, let's say I take B equals L1, I actually construct a factorized vector which gives me the A's that are connected to that B. L1, I have A's U1 to U100, which I represent them here. And then I go next to extend C, and I connect them with the B's. And then I have C1 to C100, which I connect them with, right? But I don't take this Cartesian product between these two. I just keep it like this. If I want to iterate, it's not a problem, right? I can easily iterate over them because I look at the possible combinations. Now, what it does, it goes now to the next B, okay, to the next B, and then again, it takes the vector for A. So now B is L2. L2 has U100 to U199, and then takes the C, which is C100 to C199. And that's it. So that's the way he stores internally as vectors, and then he basically works on them as vectors. So what he did is he actually said, okay, let's actually take some LDBC, which is a standard for database for graph databases with this amount of comments and so on and so forth. The system was rather modest, and says, okay, in my query, I have a condition which depends on some parameter X, which I can set such that I reach a certain selectivity on that condition. And then it compares Kuzu and Umbra, which is the system of Thomas Neumann, but this is Umbra before they added factorization, right? And now what you can see is that as the selectivity increases, of course, this means that there is more blow up in the answer. Kuzu stays relatively okay, right? Like here is a factor of 10 increase in the time, which is given by the fact that it increases a factor of 10 in the selectivity. But here, for instance, at the end, it just timed out. The one before was 230 seconds, right? So this shows that indeed this technique also makes a difference in a full-fledged system, not only in a prototype, in an academic prototype. Okay, and that's it. Thank you so much.